Alrighty, we are on chapter 5, which is all about thermal energy, and specifically we're going to be going over 5.1 today, which is about the relationship between these three concepts, this concept of temperature, this concept of thermal energy, and this idea of heat. So the first question we have to ask is about heat and temperature. Heat and temperature. What does it really mean? What does heat mean? What does temperature mean? Are they the same thing? No, they are not the same thing. They are two very different things, and I'm going to go through some examples to explain the ideas of heat and temperature to you. So first we have to refresh our minds on what matter is made of. We know that matter is made of tiny particles. The ones that we've talked about are atoms, but atoms are the tiniest, littlest part of matter. So they're the smallest part of matter. But atoms can combine. We can have two atoms together to form molecules also. So atoms and molecules, we're going to say, make up all of the different types of matter. And there's this one special type that your book mentions. They're called ions. All right? Ions are charged atoms or molecules. You're not going to really need to understand ions until we get into our section on chemistry, but just know charged means they have a plus charge, they're positive, or they have a minus charge, they're negative. So they can be atoms or molecules, but they're just a different type of atom or molecule. So we'll say that molecules are two or more atoms combined, and atoms are the smallest building block of matter. So I think I might have already given you those definitions in a previous chapter, but there you go again. So, all right. So we have to think about these tiny particles in matter and what those tiny particles are doing in matter. So in all matter, whether it's solid matter or liquid matter or gaseous matter, no matter the type of matter we're looking at, all of these tiny particles that make up the matter, they're in constant and random motion. They're always moving. All right. So like I just said, in all materials, the tiny particles that make up the matter, meaning atoms, well, I'm just going to write atoms, molecules, and ions, one of those three, whatever it is, or a mix of the three, whatever the tiny particles are, they're in constant motion, they're constantly moving, and they're moving totally randomly. So if we look at the particles that make up a chunk of, let's say, a piece of wood. Okay, if I have this piece of wood here, and I zoom way in, and I look at all of the tiny atoms and molecules that make up this piece of wood, I would be able to see that all of these little tiny particles are kind of buzzing, they're moving, they're vibrating a little bit, they're barely moving. Even though we can't see it, these little squiggly lines are vibrations. All of the particles that make up this wood are moving very slightly. So if something is moving, what does that mean about its energy? So it means that they have kinetic energy. So these particles have kinetic energy because they are moving. When they have higher speeds, like in a liquid, so we have well, we don't need to know that yet. When the particles have higher speeds, let's say we're looking at some water. In water, you don't know this yet, but I'm telling you now, the particles, think about the way that we can actually see water moving, right? We see water as fluid. It can move around. We could imagine that the particles that make up water have more kinetic energy than the particles that make up a solid piece of wood, right? These pieces up here in the wood, they're just buzzing, they're just vibrating. But in the water, they're moving around more. They're sliding past each other. They actually move from one place to another. So these particles have more kinetic energy, right? So the faster the particles are moving, the more kinetic energy they have. We know that from our last chapter. All right. So the reason we have to go through all of this is because if the particles are moving faster, these particles that make up all matter, if they're moving super duper fast, or if they're moving at higher speeds, we feel heat. So to kind of lay this all out here, the kinetic energy of particles that make up matter determine whether the object feels hot or cold. So if we have low kinetic energy of particles, let's think about an example being solid water, aka ice. Ice feels cold to the touch, right? It's a solid. All the particles that make up ice, they're moving very, very, very slowly. So when I feel ice, when I touch ice, because the kinetic energy of the particles is so low, the ice feels cold. So if we have low kinetic energy, if the particles are moving very slowly, then we have a cold feeling. And again, low kinetic energy also means low speed of particles. All right. Okay, what about medium kinetic energy of particles? Say the particles are moving at medium speeds. An example of this would be when we warm that ice up a little bit and we turn it into liquid water instead of solid water. All right, now the particles are moving a little bit faster. If I just leave a glass of water, or I leave a glass of ice in my living room and I let it sit for 4 hours or however long, eventually that ice is going to turn into water and the water is going to feel room temperature, right? So the kinetic energy of the particles has sped up because we're going from the cold ice to a room temperature or a medium heat, or not heat, but a medium feeling that we feel if we put our fingers in the eye or the liquid water, we would feel that it feels medium, right? Or room temp, you could also say. But then if I were to take that liquid water that I have in my living room and pour it into a pot and turn that pot on, put that pot on the stove and start heating it up and boiling it, steam would come off and we would have gaseous water with like steam from boiling. And if we were to feel that steam, we would burn our hands. And the reason for that is because the steam, the gas water, is traveling at a super high speed. The particles of water, the particles that make up the water are traveling at super high speeds. So the speed of particles is high. And this is why we feel heat. All right? So this is the relationship between kinetic energy and the idea of heat. But we need to now look at the relationship between kinetic energy and temperature, because as I said at the beginning, heat and temperature are not the same thing. So this is the relationship between kinetic energy and heat. Now let's look at the relationship between kinetic energy and temperature. First, we need to explain what temperature is so we're all on the same page. So temperature has a very specific definition in science. It's the average kinetic energy. It's the measurement of the average kinetic energy of the particles that make up an object that we're trying to take the temperature of. So there we go. There's a very basic definition. This is probably common sense, but the temperature of a hot cup of tea is higher than the temperature of a cup of ice water, right? So if we look at those two examples, our hot tea and our ice water, this is going to have a high temperature. This is going to have a low temperature, right? So what can this tell us about the kinetic energy of the particles? Well, this tells us that if something it has a high temperature, we also know that it feels hot, right? It has a lot of heat. If something has a low temperature, it has low heat. We know from our relationship above that we looked at between heat and kinetic energy that when something has a high heat, that means that the particles have high kinetic energy. When something has a low heat, or when something is cold, the particles have low kinetic energy. So there's a direct relationship between all three of these components of temperature and heat and kinetic energy that we're looking at here. Okay, so that's the relationship between temperature and kinetic energy. As temperature increases, so does kinetic energy. As temperature decreases, so does kinetic energy. There's a direct relationship between all three of them, though. So we can't really talk about kinetic energy without talking about both heat and temperature. There's one thing that's not in your book that we are going to discuss, and it's the units of temperature. Well, it discusses it very briefly, but it doesn't make you do anything with that information. So there's two main units that we're going to talk about. And unless you are American or you plan on studying in America, there is actually a third type of, if you're American like me, you know this third type of unit. So our first type of unit that you probably all know are degrees Celsius. I always spell it wrong. I think it's S, isn't it? Yes. Celsius. Then we have a new one, the American one that maybe you've heard of is called Fahrenheit. And this one I definitely spelled wrong. I had to look that one up. There's a weird H in the middle there. It's just everything about Fahrenheit is the worst. And that's the degree sign goes on the other side. But there's a third one that we often measure temperature with in science, and its abbreviation is K, and it's called the Kelvin. Okay, so we're going to look at some relationships. This is really important that you know this next semester or next year. For biology, you'll probably use this a little bit, but in chemistry and physics, you need to know these three units, the three ways that we can measure temperature, and you need to know how we can convert between them. So I'm going to give you explain the relationship between the three, and how if I give you the temperature in Fahrenheit, you can convert that to Celsius. Or how if I give you the temperature in Celsius, you can convert that to Kelvin. So that's what we're going to be working on also. So this is important that you take notes on this, because this is not in your book here. All right, so this is the relationship between, we're going to look at Celsius and Fahrenheit first, because that one's a little more complicated. And then the relationship, we're just going to look at Celsius and Kelvin. We're not going to worry about going between Fahrenheit and Kelvin, because we can go from, I'll get there in a second. All right, so when we go from Celsius to Fahrenheit, if we're given a temperature in Celsius and we want our answer to be in Fahrenheit, we are going to use the equation that the degrees Fahrenheit will equal 9 divided by 5 times our degrees Celsius, and that's going to be plus 32. And then if we're given Fahrenheit and we want our answer to be in Celsius, so our answer will be in Celsius. Oops, I do that the wrong way every time. Degrees Celsius. We will just flip these around. We'll have 5/9 times our temperature in Fahrenheit minus 32. So let's look at some examples. But those are the two equations for how we can solve for Fahrenheit or Celsius, and they're basically just the reverse of each other. Okay, so here's our example. A cup of water is 75 degrees Fahrenheit. What is the water's temperature in Celsius? So we are given 75 degrees Fahrenheit. So we're given Fahrenheit, and we want to convert to we want our answer to be in Celsius. So we're going to use that first equation. So let's say we have degrees Celsius, since that's what we're looking for, equals 5 divided by 9 times our degrees in Fahrenheit, right? Our degrees in Fahrenheit, right here. We were given 75 degrees Fahrenheit, and then minus 32. Oops, I've done my order of operations wrong here. Sorry. This should be this first. We need to subtract first. We subtract these first, and we get 75 minus 32 equals 43, right? We should all know PEMDAS, purple elephants marching down the street, right? So I guess here we could write on our upper equation that we have parentheses there. We don't have parentheses here on this first equation. This equation is fine, but maybe we should put, I forgot to put parentheses on this equation when I wrote it. So the big difference here between them is that this one has parentheses and this one doesn't. You don't need to worry about the parentheses. So, okay. Purple elephants marching down the street, we do parentheses first, right? So we do whatever's inside the parentheses, then we don't have any exponents, but then we multiply, okay? Okay, so let's start over, actually, sorry. So I feel like I confused you. So a cup of water is 75 degrees Celsius. What is the water's temperature in Celsius? So we're going to use this equation, I guess, because we're going from Fahrenheit to Celsius. Our answer will be in Celsius. So we'll use this equation. Degrees Celsius equals 5/9, but we're going to put parentheses, degrees Fahrenheit minus 32. So because these are in parentheses, we need to do the parentheses first. So let's plug in our degrees Fahrenheit here, which is 75. When I subtract 32 from 75, I get 43. Okay, so now I have degrees Celsius equals 5/9 times 43. When I plug that into the calculator, I get about 24 degrees Celsius. And that is my answer. Let's do another example. So here we go. A boy has a fever of 200, that's impossible. 102.3 degrees Fahrenheit. What is the boy's temperature in Celsius? So we're given degrees Fahrenheit again. So let's look at which one we should use. Erase all my arrows here. We're given degrees Fahrenheit again. So we should use this one, right? We're given Fahrenheit and we want our answer to be in Celsius. So we're going to use this same equation that we just used. So that same equation is there. And now we just need to plug in what we were given for Fahrenheit here. We were given 102.3. Then we're going to first subtract these. So 102.3 minus 32 is 70.3. Then we're going to multiply by 5/9, and that will give us our degrees in Celsius. So when we plug that into the calculator, we get a temperature of 39.1 degrees Celsius. There's our answer. Okay, let's look at a few more examples here. Okay, a swimming pool is 21.5 degrees Celsius. What is the pool's temperature in Fahrenheit? So we're given a temperature in Celsius, and we want our answer to be in Fahrenheit. So let's look over here. We're given Celsius. We want our answer to be in Fahrenheit, so we're going to use this other equation this time. We're going to use this one. All right, so if we take our C out and plug in the value we were given, we have we're going to multiply this first by 21.5. So when I'll do this part first now, since my order of operations says to do multiplication, then addition. Whoops, I forgot. Right? Addition is down here. So we do multiplication first. So we have to do this multiplication problem first, or this part of the problem first. And we get 38.7, and we're going to add, now do our addition part, and we get 38.7 plus 32. So our final answer is 70.7 degrees Fahrenheit. Okay, let's do one more example with Fahrenheit and Celsius. All right, so on a super hot day, the thermometer reads 49.9 degrees Celsius. Outside, what is the temperature in Fahrenheit? So we're given a value in Fahrenheit, and we want our answer to be, we're given a value in Celsius, and we want our answer to be in Fahrenheit. So if we look up here, we're going to use the same one again. We're going to use this one because we're given Celsius and we want to find our answer in Fahrenheit. So let's use the same equation. So if I write the equation, then we can erase the C and plug in our actual value that we're given. I'm going to multiply here, 49.9. I'm going to multiply first because of the order of operations. And when we do that, we get 89.8. Then we're going to add 32 to that. And we get an answer of 122 degrees degrees Fahrenheit. All right. So there we go. That would be our answer for that one. So this is the simple way to convert between Fahrenheit and Celsius. And now we're going to look really quickly before I end this lecture at the relationship between Celsius and Kelvin. And it's way simpler. It's way easier than Fahrenheit and Celsius. All right. So our relationship here is if we are given, let's do Celsius first. If we're given Celsius and we want to convert to Kelvin, so if we're given this and we want our answer to be in Kelvin, we are going to have an equation that says degrees Kelvin equals degrees Celsius, whatever we're given, plus 273 equals the temperature in Kelvin. Super easy. If we're given the opposite, if we're given Kelvin and we want to go to degrees Celsius, we will use this equation, the degrees Kelvin, or the amount Kelvin, minus 273. So let's look here at some examples. Answer. Okay, an ice cube has a temperature of 1.5 degrees Celsius. What is the cube's temperature in Kelvin? So we're given degrees Celsius, and we want our answer to be in Kelvin. Given Celsius, answer in Kelvin, we're going to use this equation. So let's write that down here. We have Kelvin equals, look back up there again, we're going to do degrees Celsius plus 273. So the degrees Celsius that we were given is actually a negative, and we'll do negative 1.5 plus 273. And we get that our degrees, well, we don't have to write it like that. This equals 271.5 Kelvin. See, that's much easier than the Fahrenheit and Celsius one. Okay, let's look at one more example with Kelvin and Celsius here. All right. Average body temperature of a human is 310.2 Kelvin. What is the average body temperature in Celsius? We are given something in Kelvin, and we want our answer to be in Celsius. So if we look up here, we are given Kelvin. We want our answer to be in Celsius, so we will use this equation. So, degrees Celsius equals Kelvin minus 273. If I plug in here my degrees Kelvin that I'm given, of 310.2, and I plug all this into a calculator, I get that the average body temperature is 37.2 degrees Celsius. There we go. Okay, so that's where we're going to stop today. We talked about the relationship, how heat and temperature are not the same. Heat is what we feel, and the temperature is the measure of the kinetic energy, remember? So we looked at all of how matter is made up of tiny particles, and all of those particles are moving, even in something that seems like it wouldn't have particles moving, like a piece of ice or a piece of wood. There's still kinetic energy in all of those particles. We looked at the relationship between kinetic energy and this idea of heat, and we said that the higher the kinetic energy, the faster the particles are moving, and therefore the hotter the object feels, the more heat the object has. The lower the kinetic energy of the particles in the object means that the speed of the particles is slower, and so therefore it has less heat or it feels cold. Then we looked at the relationship between kinetic energy and temperature and kind of mixed heat in there too. And we said that as temperature increases, or as kinetic energy increases, so does temperature. And when temperature and kinetic energy increase, the object feels hotter. As temperature and kinetic energy decrease, the object feels colder. Remember that as kinetic energy goes down, so does temperature. As kinetic energy goes up, so does temperature. And finally, we looked at the different units that we can use to measure temperature. We said there are 3 main units that we're going to need to know and be able to convert between: and Celsius, Fahrenheit, and Kelvin. Then we looked at the relationship between converting Celsius and Fahrenheit, between those two. So if we're given Celsius and we want to go to Fahrenheit, we use this equation. And if we're given Fahrenheit and we want to go to Celsius, then we use this equation. And remember, it's very important that we put the parentheses in here first, and we do the parentheses first, otherwise we'll get the wrong answer. Then finally, just now, we looked at the relationship between Celsius and Kelvin, and we have these two, I want to erase that line. These 2 equations that we can use when we're given Celsius. We can use, and we want to convert to, or have our answer be in Kelvin. We use this equation. We just add degrees Celsius plus 273. And when we're doing the opposite, when we're given Kelvin and we want our answer to be in Celsius, we use this equation. Okay, so for the remainder of the period, you can work on the in-class questions. They will be due tomorrow, and tomorrow's Wednesday. We will finish 5.1 tomorrow. On Thursday, if anyone requests it, we can have a brief Zoom review on Thursday before your quiz that's on Friday, if you want that, but you have to ask or say, yes, I would like that. Reach out to me and let me know that's something you'd be interested in. Otherwise, we will move on to the next chapter, or not chapter, but the next section on Thursday, and then your quiz will be on Friday over chapter 4. So please let me know if you have any questions about anything I just went over. Please let me know if you think you need another review on Thursday, and that is it. Thank you.